How's it going, everyone? Hope everyone's had a good day so far. Do you all have any questions over section 5.2 before we continue? Okay. So today, I think we're going to be able to cover sections 5.3 and 5.4. So we'll do both of those together. And the plan is for next week, do 6.1 and 6.2 on separate days. And then the week after that, review and then test over chapters 5 and 6. Okay? So plan on 2 weeks from today, the 28th, we'll have a test on chapters 5 and 6. Well, not exactly on that day because you'll have that whole window of opportunity. So, anyway, um, but thereabouts, basically. All right, so section 5.3 covers, here we're talking about independence and the multiplication rule. Last time we looked at the addition rule, and today we'll be looking at the multiplication rule. Now, what we look at in this section 5.3 is kind of a simplified version of the multiplication rule, but we look at the general multiplication rule in section 5.4 after this. And that's kind of why I like to do both of the sections on the same day, is that it covers a lot of the same concepts, but it approaches from two different directions. Section 5.3, where the events are independent, and then section 5.4, where there may not be the case. Okay. So let's look at independent events first. So, so two events, E and F, are independent. That's a T, sorry. Independent if the occurrence of one of the events does not affect the occurrence of the other event. So that means that one outcome has no impact on the other outcome. So if we were to flip a coin and roll a six-sided die at the same time, then whether or not the coin landed on heads, it doesn't impact the outcome on the die, whether if we roll a 1, 2, 3, 4, 5, or 6. Okay? So there's no connection between the two things. It's basically what we're saying. If we what's a good way to say this? Two events are dependent if one does influence the other. Now, any time we have what are called classical probabilities, as long as we're doing them separately, like we're just if we roll two dice, a pair of dice, what when the first die lands on doesn't impact the second die. Now, somewhere where we may have events be dependent, if we have a jar full of jelly beans, for instance, there's 50 cherry jelly beans and 50 grape jelly beans, for instance. If we pick one jelly bean at random out of the jar and eat it, now there are less jelly beans in the jar. So if we pick a jelly bean at random, eat it, and then pick again, the probability of getting a certain jelly bean on the first try is different than the probability of getting the same colored jelly bean on the second try, because we've reduced the number of jelly beans that are in the jar. In that case, the events are called dependent, and because one is absolutely influencing the other. If we take a cherry jelly bean out of the jar and eat it, there's only 49 left, and our probability of choosing cherry just decreased. Okay. So when we talk about independent events, we're saying that there is no influence of one on the other. Alright. So now we have a multiplication rule for independent events. And for our multiplication rule, we'll say that if E and F are independent, then the probability of E and F is equal to the probability of E times the probability of F. In this case, we just multiply the two probabilities together. Now, that only applies if they're independent. If they're dependent, we have a different rule that we'll look at in the next section. Actually, the rule in the next section is what we call the general formula. But anyway, so that's what we can say here. So the idea is that, okay, since flipping a coin and rolling a die have no influence on each other, then the probability of the coin landing on heads and the die landing on a 5, for instance, we just take the individual probabilities. Probability of a coin lands on heads, 1 out of 2. Probability of a die lands on a 5, 1 out of 6, and multiply those together. Okay. So let's say event E is we flip a coin. Well, we flip a coin and roll a die. So for our event E is that coin lands on heads. And event F is that the die lands on a 5. We know the probability of a coin landing on heads is 1 in 2 chance. Okay. There's only one option where it's successful, and that's where it lands on heads. But we know there's 2 options total that it could be heads or tails. So 1 in 2 chance of that probability. For a die, we know that we roll a die, there's 6 options. 1, 2, 3, 4, 5, 6. Only one of them is a 5 though, so it's a 1 out of 6 chance, or 1/6 probability that event F is successful. So if we want the probability of E and F, that the coin lands on heads and the die lands on a 5, we know that we just multiply those 2 probabilities together that we just found. So 1 over 2 times 1 over 6. And if we're multiplying fractions, this is something that will come up in this section and the next one. Multiply the numerator times the numerator, so 1 times 1, and then the denominator times the denominator, 2 times 6. Okay, so just multiply across, top and bottom. Okay. So the chances of this occurring, that we flip a coin and roll a die and it lands on heads and a 5 respectively, we end up with 1 out of 12 probability. Okay. Continuing from there, let's see. Now, this is on page 277, looking at number 12. What is the probability of obtaining 4 ones in a row when rolling a fair 6-sided die? Okay. Anytime we have something being repeated, just like when we saw the multiplication rule for 2 items, the same thing applies if we have more than 2 items. Each of the die rolls here are considered independent events, and so we'll find the probability of each and then multiply all 4 of the values together. So we have our first die roll, our second, our third, and our fourth. And so what is the probability that we would roll a 1 on a fair die? One out of 6? Now, does that probability change for any of our other rolls, or is it still going to be 1 out of 6? Yeah, it'll just stay the same for each time we roll the die. Every time we roll the die, it'll be 1 in 6 chance of landing on a 1. Okay? And so we just multiply these together because the multiplication rule for independence says that if we repeat this event, we just multiply the probabilities together for each individual event. So each roll of the die is considered a different event, basically. So multiplying these together, and we have 1 times 1 times 1 times 1, and we know that's equal to 1. We don't have to do a lot of calculation for that. On the bottom, we have 6 times 6 times 6 times 6. One thing that we could do here, and I don't know how familiar or comfortable you are with exponents, but instead of saying 6 times 6 times 6 times 6, we could write that as 6 to the 4th power. And then we can go into our calculator and we'll enter 6 raised to the 4th. Now on the graphing calculators, it's 1 in 6 because there's 6 numbers that could come up when we roll the die, and they have an equal opportunity to occur. So only one side shows a 1, so 1 in 6 chance of rolling a 1. But it's repeated as 1 over 6 each time because they are independent. I'm not quite sure which one you were talking about, but hopefully I answered the question from all angles. Okay. So we do 6 to the 4th power, and again, here's our caret button that does our exponent, and we get 1 over 1296. Now we could leave it like that, or if we prefer, we could actually calculate out the decimal. Now, when we see the decimal here, notice it says e minus 4 at the end. Now, I'm just going to write down 7.716 e minus 4. What this means is basically a scientific notation is what is being used here. So when it says e minus 4, it means times 10 to the negative 4. And so what that number actually is 0.0007716. Okay. So that means we'll want to move the decimal 4 places to the left. So from after the 7, we go 1, 2, 3, 4 places to the left. We have some empty spaces here. We fill them in with zeros. That's one thing that we'll start to encounter on our calculators and for various problems, is that if our probability is very small, as it is in this case, 1 in 1,296 chance, then frequently we'll see this e to the minus 4 notation show up on our calculator. And so that's just our scientific notation. That's how it displays numbers as scientific notation. So we just have to interpret it from there. Okay. Now I want to talk about our conditional probability one more time, and we introduced the concept of conditional probability in section 2. Let's talk about it a little bit more before we move forward. Not conditional, sorry. Complementary probability. Probably you're wondering, what the heck is he talking about? And you'd be right. Complementary probability We introduced that at the end of section 5.2, and again, the idea was that the complement contained everything that was not in the original event. So if we have an event E that has one outcome, then event E complement has all the other outcomes besides that one. Okay? Now, complementary probability says that probability of E plus probability of E complement is equal to 1. And that's where we ended last time with. And we said that we could turn that around and say the probability of E complement is equal to 1 minus the probability of the original event E. Alright, now here's how we plan on utilizing this. There's a number of ways that we could utilize this, but this is the one where we primarily see it being used. If we want the probability that at least one of something happens, whenever we see at least one, like if we roll a die 5 times, then at least one of the numbers is a 6. That means one number could be 6, two numbers could be 6, 3, 4, or 5. And calculating those as they are, we have to do each one individually and add them all together. And it's a really complicated process. But the problem becomes a lot easier with complementary probability, where we think of what is the complement of at least one. What is the opposite of getting at least one of a certain number when we roll the dice? Does anyone have an idea? So if our event, let me clarify a little bit. If our event is roll at least 1 6 on 5 dice, what would be the complement of that event? Anyone have any ideas? Well, you might have an idea, but maybe you're not feeling confident, and that's okay. 1, 2, 3, 4, 5. Yes. That's good. That's a good point, because the opposite of rolling at least 1 6 is that we don't roll any 6s, that we get all of our numbers are 1, 2, 3, 4, or 5. So a better way of saying that, rather than just listing out the different numbers, is roll 0 6s. Okay. So either we roll 1 or more 6s, or we don't roll any 6s. Those are the two complements. Those are the two different outcomes in that scenario. Okay. So the way that we like to summarize that is, if we want the probability that at least one of something happens, then the complement of that is that none of those things happen. Okay. If it's 1 or more, then the opposite is 0. Okay. So either we get 1, 2, 3, 4, 5 6s, or we don't get any 6s. Okay. And that's what we're getting at here with our complementary probability. So probability of at least one occurring is 1 minus that probability that none occur. So we can more easily calculate this probability of E by calculating this other probability much more easily, the probability of rolling 0 sixes on 5 dice. Now our probability that we don't roll a 6 at all, that means on the first one, if we don't get a 6, how many numbers could we possibly get? How many numbers in the die are not 6? Okay. We're thinking about how many numbers are not 6. Well, there's 5 other numbers besides the 6. Right. So we have a 5 in 6 chance that we don't land on 6. As long as we land on one or the other 5 numbers, we haven't gotten a 6. So 5 in 6 chance we do not land on a 6. That's true for the second roll. 5 in 6 chance we do not land on 6. That's true for the third, fourth, and fifth as well. Now, whether or not we get a 6 in each roll, we know these events are independent, so we can multiply their probabilities together. So, we want 5 over 6 times itself 5 times. And again,